In the last session, we've been talking about fixed fields of a collection of automorphisms on a field. The result was like this. If E is a field and S is a collection of automorphisms, then the set containing the elements from X in E such that it is not moved by any of the automorphisms from this collection is a subfield of E and is called the fixed field of S or the collection. So this is what we found in the last session. Let's do an example of a fixed field. Let's assume that E is equal to Q of root 2 comma root 3 comma root 5. Then we are going to define two automorphisms. Actually, they are conjugate isomorphism, but it is going to be an automorphism. So it's psi of root 2 comma minus root 2 and psi of root 5 comma minus root 5. This actually goes from root 3 comma root 5 of root 2 to root 3 comma root 5 of minus root 2. Basically both are E's, that is from E to E, and it is defined by a psi of root 2 comma minus root 2 of the elements of E. Elements of E is going to be C0 plus C1 root 2 plus C2 root 3 plus C3 root 5 plus C4 root 10 plus C5 root 15 plus C6 root 6 plus C7 root 30 equal to, this is a general element of this. Okay, so this is going to be C0. Wherever you have a root 2, you will replace that root 2 by minus root 2. Minus C1 root 2 plus C2 root 3 plus C3 root 5 plus here there is a root 2. So it is going to be, it's going to be minus root 10, C4 minus root 10. Then there is no 2 here, so it remains same. Root 15 minus C6 root 6 minus C7 root 30. And here this is going to be q root 3 comma root 2, or let's take it as root 2 comma root 3 of root 5 to q of root 2 comma root 3 of minus root 5, and that's again from e to e, defined by psi of root 5 comma minus root 5 equals of c0 plus c1 root 2 plus c2 root 3 plus c3 root 5 plus c4 root 10 plus c5 root 15 plus c6 root 6 plus c7 root 30 equals c0 plus c1 root 2 plus c2 root 3 minus c3 root 5 minus c4 root 10 minus c5 root 15 plus c6 root 6 minus c7 root 30. Now our objective is to find the fixed field of psi of root 5 comma root minus 5 of root 2 comma minus root 2. Minus root 2. And the definition is there is only one automorphism in this collection. So those elements from E that are fixed by this automorphism. So 5 comma minus root 5 of root 2 comma minus root 2 of x equal to x. And this ever x belongs to, yeah, that is right, but here to write x comes from E. And the general element of E is again this. So this is going to be x belongs to E such that psi of root 5 comma minus root 5 of x is again the same, and when you expand with root 2 minus root 2, this is going to be c0 minus c1 root 2 plus c2 root 3 plus c3 root 5 minus c4 root 10 plus c5 root 15 minus c6 root 6 minus c7 root 30. That is equal to x. And that is equal to x means what? That is equal to c0 plus c1 root 2 plus c2 root 3 plus c3 root 5 plus c4 root 10 plus c5 root 15 minus plus c6 root 6 plus c7 root 30. So if this is equal to this, what does that mean? That is equal to x belongs to E such that, expand this again, that's going to be C0, no change here, no change here, this is going to be C3, C5. This actually turns back to C4, C10. This is actually minus C5 root 15. This no change, C6 root 6. This you are going to turn back to root 7, 30. Equal to C0 plus C1 root 2 plus C2 root 3 plus C3 root 5 plus C4 root 10 plus C5 root 15 plus C6 root 6 plus C7 root 30. So this has to be equal. Then those x belongs to this fixed field. So that is going to be x belongs to E. This x is again the same thing. C0, where x is equal to, we can say x is equal to C0. This has to be 0. Then only this will be equal. Same thing, this has to be 0. This has to be 0. And this has to be 0. So C0 plus C2 root 3, this goes plus C4 root 10, then plus C7 root 30. So this is the format of where Ci comes from Q. So that is actually equal to E 5 comma minus root 5 of C of root 2 comma minus root 2 is equal to C0 plus C root 3 plus C C2 root 3 plus C4 root 10 plus C7 root 30, where Ci belongs to Q. But you can derive root 30 from 3 and 10. So we can discard this. So this is going to be, if you take it as A plus B root 2 root 3 plus C root 10, where A, B, C belongs to Q. And what is this? This is going to be Q of root 3 comma root 10. Now we'll let G be a collection of all automotive automorphism on a field E. Then let us take two elements from here. Let sigma comma tau belongs to G. These are automorphisms. So that implies sigma after tau is also an automorphism. That implies sigma after tau belongs to G, because G is the collection of all automorphisms. Then when sigma belongs to G, then sigma inverse belongs to G, or sigma inverse is also an automorphism. Implies sigma inverse belongs to G. And I belongs to G. I means where I is the identity automorphism. So that implies G is a group. So the collection of all automorphisms on a field is a group under composition. Here the binary operation is composition. So the collection of all automorphism on a field E, or on a field is enough, is a group under composition. Now, if G is a group, then and if it is a finite group, then an element A in G is of order n if a to the power of n is equal to the unity of the group, and a to the power of m is not equal to 1 for m less than n. So that is a definition of order. So let us consider an automorphism and find out its order here. So let E equal to, again, I'm going to take root 2, root 3, root 5, and sigma, I'm going to take it as root 3 comma minus root 3. So this is actually from Q of root 2 comma root 3 comma root 5 to Q of root 2 comma root 3 comma root 5. It's actually from root 2 root 5 of root 3 to root 2 root 5 of minus root 3, but I'm not going to write it like that. So instead of writing the whole term, what I'm going to do here is, let us write like that only. So let's start from here. Root 5 of root 3 to q of root 2 root 5 of minus root 3. There is an advantage like that. So the sigma of what is an element here? I'm going to write it like this: a plus b root 3 is equal to a minus b root 3, where a comma b belongs to q of root 2 comma root 5 instead of q. So this again, when you expand it, you'll have the whole 7 fields, seven elements here. So what is so this is a plus b root 3 is equal to a minus b root 3. So what is alpha square, sigma square of a plus b root 3 is equal to sigma of a plus a minus b root 3, because this is again sigma, so that is equal to a plus b root 3. So sigma square is equal to I, because sigma square of a plus b root 3 is equal to a plus b root 3. That implies the order of psi root 3 comma minus root 3 is 2. And similarly, you can say the order of psi of root 2 comma minus root 2 and psi of root 5 comma minus root 5 is 2, are same and equal to 2. We will do one very simple problem to get familiarized with the conjugate isomorphisms and composition of automorphisms. So let's take E is equal to Q of, same thing, Q of root 2, root 3 and root 5. And let's compute psi of root 5 comma minus root 5 square of psi of root 3 comma minus root 3 of psi of root 2 comma minus root 2 of root 2 plus root 45. This is an element, this actually is from this composition is from E to E. Root 2 plus root 45 is from E. And each of these are automorphisms, so composition is also in E. So this is going to be psi of root 5, so this is going to be equal to psi of root 5 comma minus root 5 square of psi of root 3 comma minus root 3 of, here you replace root 2 by minus root 2 plus root 45. There is no root 2 here. This is going to be psi of root 5 comma minus root 5 square of, replace root 3 by minus root 3. There is no minus root 3 here, so here there are two root 3's. This is actually you can write it as 3 root 5. 3 root 5. Let's make it like that. So there is no root 3 here. So it is going to be 3 root 5. But you know that the order of root 5 minus root 5 is identity. So this is going to be, we don't need to even compute. So this is going to be root 2 plus root 45. I'm going to write it back to the same format. Because psi of root 5 minus root 15, because the order of psi of root 5 comma minus root 5 is. So this is the result. Just to get familiarized with the conjugate isomorphisms and the composition of automorphisms. Now we are going to get into an important theorem on automorphism. So let E be a field, and for the sake of convenience, I am drawing the field twice. Both are the same field E. And we know that the collection of automorphisms from E to E on E, sigma 1, sigma 2, sigma 3, etc., forms a group under composition. And let us assume that there is a subfield of E. This is F and this is same F. Now we are looking for the automorphism that leaves F fixed, meaning some of this automorphism does not move an element from F so that means it is mapping X to X, some of them, not all. So we are interested in only those automorphisms. So let us assume that let G prime be a collection, be the collection of automorphism on E, on a field E, field E, that leaves a subfield F of E fixed. We are going to use a different notation for this G prime after we see what kind of collection is this. So G prime is equal to automorphism on E that leaves F fixed. So let us take two elements from here. Sigma 2 belongs to G prime. That implies sigma of A is equal to A and tau of A is equal to A for all A in F. So, sigma after tau of A is equal to A for all A in F because it is not moved. And that implies sigma after tau belongs to G prime because G prime is the collection of all automorphisms that leaves the subfield fixed. Now, sigma belongs to G prime implies sigma of A is equal to A. That implies A is equal to sigma inverse A, and that implies sigma inverse belongs to G prime. And definitely the identity automorphism belongs to G prime because I of A is equal to A. That implies G prime is a group, is a subgroup actually, is a subgroup of all automorphisms on E. Subgroup of the group of all, subgroup of the group of all automorphism on E. And this subgroup is called the group of automorphism on E over F, or simply the group of E over F, and is denoted by G of E over F. So it is, we are changing the notation of G prime. We started off with G prime, but this is the notation we are going to use later on. This means the group of all automorphism on E leaving the field F fixed. It's a subgroup of all automorphism on E. Don't confuse with the quotient, because this is not the quotient of E over F. E and F are fields here. So, and we are not considering the quotient ring or quotient field or quotient group here. It is just a notation to identify the group of all automorphisms leaving F fixed. So let E be a field and F is a subfield of E. Now what is then G over F? The group G over E over F is the automorphisms on E that leaves F fixed. Now, what is the fixed field of what is the fixed field of G of E over F? See, these are a collection of automorphisms, and we are going to find the fixed field of automorphisms, the fixed field of these automorphisms. So that is actually x belongs to E such that sigma of x equal to x for all sigma in G of E over F. If you take any element from this subgroup, and when you compute an element of E, then that should be that element. That should leave that element fixed. And that is what is called the fixed field. Now let us assume, let x belongs to F and sigma belongs to G of E over F. What does that mean? That means sigma of x equal to x, because this is F and you are actually fixing F by every automorphism from this group. And what does that mean? This means that, see, this means that x belongs to E of G of E over F. Because, so all elements of x, see this x, this fixed field contains all x that are fixed by elements from here. And this is an element here, and this is x. Whether it's in E, if it's in E, if it's in F, it's already in E. So this is actually x belongs to E and sigma of x equal to x. This condition is satisfied. That means x belongs to here. So that implies F is a subfield, a subgroup of a subfield of the fixed field G of E over F. So the result is, let E be a field and F a subfield of E. Then the group of E over F, or the collection of automorphism, the collection of all automorphism on E that leaves F fixed is a subgroup of all automorphisms on F, also on E, and F is a subfield of the fixed field of G of E over F. So this is the result. This is a very important result. E is a field and F is a subfield, and if you collect all the automorphisms that leaves F fixed, it becomes a subgroup of the group of all automorphisms, and always F is a subfield of the fixed field of the group of automorphism on E over F.